Hi, my name is Tom Dick. I'm a mathematics professor and a math advisor for Texas Instruments. This video is part of the TI-Nfocus AP Calculus series. Here we're going to use the TI-Nspire to explore particle motion in the coordinate plane. That's a BC topic, and we'll draw for illustration the example of free response question 2 from the 2021 AP BC exam. Now in another video, Steve Kokoska goes into detail how to calculate answers to the various parts of this question using the TI-Nspire. In this video, we're going to be using the TI-Nspire for a special visualization of the acceleration and velocity components. Let's review what that question asked. We're given a particle p moving in the xy plane, and we're not given the position functions, but we're given the velocity vector and an initial position of -2, 5. Part A, we're asked to find the particle's speed and acceleration vector at time t equal 1.2. In Part B, we're asked to find the total distance traveled by the particle over that time interval from 0 to 1.2. And then finally, in Part C, we're asked to find the coordinates of the point at which the particle is farthest to the left for t greater than or equal to 0, and explain why there's no point at which the particle is furthest to the right. Now, in this particular file, we're going to set up a nice visualization that's dynamic. Here's how it's going to work. On the next page, I'm going to define the x and y components of that velocity vector function for the particle p. Then we'll use those velocity functions to define the corresponding acceleration and position component functions. On page 1.7, we'll have a dynamic numerical and graphical display of position, velocity, and acceleration, with a slider that lets you control time t. Alright, here on page 1.6 you can see I've taken the given velocity components for the position and defined those as Vx and Vy, and then we differentiate those velocity components with respect to time t to get the acceleration x and y components. To find the position x and y coordinates for the x coordinate position px of t, we'll take the initial x coordinate of -2 at time 0, then we'll look at the net change in x coordinate by integrating the velocity x component from 0 to t and add that on. Similarly, for the y position coordinate, we take the initial y coordinate of 5 at time 0 and then add on the net change in y coordinate represented by the interval of velocities y component. Now on page 1.7 here, we have that display of point P, and here's its initial position at time 0, -2, 5. We also have a numerical display of the velocity and acceleration vectors. Here you can see the velocity is -1, 0, and acceleration is 1, 0. These are also graphically displayed. Notice this green arrow is representing velocity. It's pointing straight to the left and has a length of 1 unit, while the acceleration vector has a length of 1 unit but is pointing directly to the right. Here we have our slider that will control time t. Now before we start incrementing time forward, let's consider what that initial velocity and acceleration suggests about how the particle p will start moving. The velocity vector pointing directly to the left suggests that particle p will start moving directly to the left. Let's increment time by 0.1 units, and we can see, yes, the particle p has nudged to the left a little bit. The velocity and acceleration, though, have now changed, and we can see the velocity vector is pointing upwards and to the left, and the acceleration vector is indicating how the velocity vector will continue to change. When I reach t equal 1, I notice that the x-coordinate of the velocity is now 0. Now recall we were looking for a position of the particle when it's reached its leftmost position, so this may be significant. In fact, that acceleration vector suggests the velocity is going to start turning to the right. So this position right here may be that leftmost position we're looking for. I'm going to increment time forward to 1.2. At that time, we were asked to find both the speed and acceleration of the particle. The acceleration components are right here at the bottom of the screen. To find the speed, we can measure the length or magnitude of the velocity vector. And that's this 1.27 units. Now that's not quite accurate enough for AP purposes, so let me bump up the precision that's displayed here. And so that's a measure of the speed of the particle at that time. All right, let me go ahead and delete that speed measurement, and we'll move over and continue to increment time. You'll notice how the x component of the velocity and acceleration are really growing quickly. And the particle is really moving fast now toward the right, while the y components stay relatively close to zero. You look at the components of the velocity and acceleration functions as functions, you can make sense out of that. All right, I'm going to back up now, move the time back to 0, and illustrate a couple of other things we can do with this file. One is we watch the particle dynamically move, but we might want to see a picture of the path that it traces out. So I'm going to go to Trace and choose Geometry Trace. And now I'll select the point P. And what this will do is as I increment time, the point P is going to leave a trail behind of the positions it's occupied. And as you can see, the distance between the points for these equal time intervals is increasing. That's an indication of the increasing speed of the particle as we move forward in time. Okay, now I'm going to back the time up to 0 again, and we'll look at another way of illustrating the path of the particle. First of all, let me go ahead and erase that geometry trace. And then once we've done that, what we'll do is pull up the parametric plotter. So I'll go to the menu and go to Graph Entry Edit, choose Parametric, and now that we have the parametric plotter up, we can enter the position x and y components in for x1 of t and y1 of t here. So I've entered the position functions, and now let me change this time interval from 0 to, it looks like it was at 2 pi, we'll set it to 0 to 3. I'm going to make the t-step equal to 0.1. Now using the parametric plotter, let's see what kind of path we get. And there we go. And we still have an active time slider that's now moving the point with the displayed velocity and acceleration vectors along this curve. By the way, at any point, the velocity vector's slope is the slope of the tangent line to the curve, but the velocity vector also indicates what direction we're moving along the curve. So it gives us more information than just the slope. Going ahead to increment the time. So we've got lots of ways now to visualize the motion of the particle along this path and the velocity and acceleration vectors. Well, that winds up this video. For more resources like these, please go to education.ti.com.